This video is the final section on transport category aircraft electrical systems. And today I'm going to talk about secondary electrical sources as well as backup and emergency sources. Earlier we talked about engines being the primary source. So when a transport aircraft is in flight, it's going to look for power from an engine generator first. Secondary sources are those that it's going to look for after that, or say there was an engine failure or a generator failure. You can use one of these secondary sources as a second power supply during flight. So the APU generator is the first of these, and these are a three-phase in larger transport category aircraft, so AC aircraft. These are a three-phase 120 volt 400 hertz generator, and they mount directly to the APU gearbox. And with the APU, they don't have a constant speed drive. Many of them are rated to the same current capacity as the main IDGs on smaller aircraft. Larger aircraft, they oftentimes won't be able to power everything, or in some cases there are two of these mounted to a single APU. But ultimately, the frequency, because they don't have a secondary, or they don't have a constant speed drive, the frequency is controlled by the APU speed. And with APUs, auxiliary power units, when they're operating, we'll talk about those in a later lesson. They're a small turbine engine. In addition to the main engines on an aircraft, they're a small turbine engine that typically can be started using a battery DC starter. And they are designed to drive, their primary purposes are to drive electrical generators and then also be a bleed air source for operating bleed air, for powering bleed air operated components on the aircraft. And when an APU is started, it starts up, it runs to 100%, and it essentially has a constant speed that it runs at. It doesn't vary like engines do. And so we don't need that constant speed drive, because the APU and the APU generator are designed to be mated together, and the APU generator when on an APU that's running at 100% will put out 400 hertz. Another secondary source that you'll commonly see is a hydraulic driven generator. Again, these are three-phase, 120 volts, and they're going to put out a 400 hertz on most transport aircraft. If you have some of the latest ones that use wild frequency, they still probably are going to put out 400 hertz, because that's still kind of the standard frequency point that we're shooting for. But what these are is a hydraulic motor. So hydraulic fluid is pumped through a rotary motor that's coupled with a generator very similar to the APU generator. Again, they don't have any kind of a constant speed gearbox. The hydraulic motor is designed to run at normal system pressure on most transport aircraft, 3,000 psi or whatever the design pressure is, and flow. So the pressure and the flow, and then the flow through the motor, are kept constant just by their design in the hydraulic system. And so they'll drive these small generators at a constant RPM. And so that puts out that 400 hertz. These oftentimes are limited in capacity. They're not going to be able to power entire aircraft, but they are going to be able to power a significant amount. In some cases, they can power an entire bus, one of two buses or three or four buses, depending on how the aircraft is configured. But often then if they're by themselves, they're going to power only essential equipment. So those are kind of the two secondary sources that we'll see on an aircraft when it's in the air. Now we're going to get into the emergency sources, and there's a couple different versions of these. So there's two primary emergency two emergency sources that are the most common. The first is an air-driven generator, like what's shown in these pictures here. So these are two slightly different ones. The one on the top, I believe, is a CRJ, and I can't remember which model. The one on the bottom, going off memory, I believe is off an Airbus, probably an A320 or something like that. But these are air-driven generators. They're made up of two parts. They're made up of a ram air turbine, which is also known as the acronym RAT. And then that ram air turbine is coupled to a generator. And again, these are three-phase, 120 volt, very limited capacity, so limited load capacity. And they're 400 hertz. And the blade pitch is variable on them. And so the RPM, so these are going to be spun by the airstream. So in a case where an aircraft has lost power or lost engines and APU essentially has no source to generate electrical power, this pops out of the side of the airplane. They're normally inside that little door that you can see on each of these pictures. It pops out into the airstream as the plane is gliding, and the air passing over the turbine blades causes them to spin. And what they have is in the dome, at the front, you can see there's a dome there. They'll be able to control it. We'll look at them a little bit closer, but they have a flyweight system that can control the blade pitch in order to ultimately control the RPM of the turbine, which keeps the RPM of the generator constant to get that 400 hertz. These only power the most critical equipment. In many cases, it's one or two of the ICAS displays. It's going to be maybe a single hydraulic pump, a few other a single radio, and they are pretty much there to allow the airplane to give the airplane power to glide to the ground. At this point, you don't have any engines, and so or all electrical systems. Even if the engines are running, all electrical systems are out, but they're going to provide enough to be able to safely guide the airplane back to land as best as possible. But they can, most of the time they deploy automatically. They have a computer system on them that senses a total electrical failure and they'll deploy automatically. However, they do utilize in the flight deck, there is a provision to be able to deploy them manually if the need be. So looking at them in more detail, here is a little bit closer ADG, air-driven generator, and first off circling the generator in the back half there. It's mounted to a strut that comes out of the side of the airplane. It is air-cooled. There's vents on the front which are air-cooled, and then it's coupled to the ram air turbine, which is the forward part. And the internal governor, that's that forward dome area I was mentioning earlier, has a set of flyweights in it, which if the turbine starts to spin too fast, it can make the blade pitch finer in order to slow it down. If the turbine is spinning too slow, it can vary the blade pitch in order to increase the RPM. And so what it's trying to do is maintain a constant RPM, a constant speed, so that the generator frequency output is maintained constantly. The other thing it's doing is as the generator load increases, which will try to slow as the electrical load on the generator increases, that would try to slow the generator down. Or as the electrical load on the generator decreases, which would allow it to speed up, they're going to compensate for those changes as well to try to keep the speed as constant as possible. And so it will do that as long as needed until the airplane is, essentially from wherever the airplane is until it lands and hopefully lands safely. The other common emergency source you see, and this is what the 727 has, and it's not something you can necessarily see, it uses parts we've already talked about, is a battery, a DC 28 volt battery that connects to a inverter, a static inverter. And an inverter it's a solid state device that takes a DC input and it produces an AC output, an alternating current output. So in this case, the inverter is wired to a hot or an emergency battery bus. And then it comes on again. The battery's going to have a limited capacity, and the more load that's on it, the shorter it'll be. The less load that you have on it, the longer it would potentially last. But you're going to convert that DC, that stored DC from the battery, into a three-phase, 120 volts, 400 hertz AC. to power a minimum amount of equipment to be able to keep the airplane in flight, or to glide the airplane as it might be. These systems, when they're built, have to have a minimum of 30 minutes supply power for 30 minutes at a reduced load. And however, if you have aircraft that are ETOPS certified, so extended twin operations, which is where aircraft are flying over open bodies of water for extended periods of time. There are certain, depending on the ETOP certification level, this time period will be longer, with the idea that a plane that's further away from land is going to need to have this power available for a longer period of time. But at minimum, they're going to supply 30 minutes at a reduced load for aircraft that don't fly over water for extended periods of time. In order to get that, so in this case, in order to get that minimum of 30 minutes, or in the case of the air-driven generator, to be able to match the load to the limited capacity of the generator, the electrical system is going to have the ability to load shed, or emergency load shed. And that is, the electrical load overall needs to be reduced in order to match the power that's available from either the static inverter or the air-driven generator. And so, in the case of the static inverter, we need to extend the life of that emergency source so it meets the minimum 30-minute requirement. This is what I was talking about earlier, the air-driven generator. The only things that may be powered in these situations are your most basic flight instruments. Again, enough to be able to do some navigation for a limited period of time, considering you're probably not going to be flying very far than this configuration. Be able to control the airplane, maintain directional control, which is what the hydraulics, with hydraulic driven flight controls, you have to have some form of hydraulics in order to operate the flight controls. And potentially drop landing gear, although oftentimes that's done assisted with gravity, so you don't have to have quite as much capacity there. And again, along with the flight instruments, it could include things like navigation instruments and radios. Obviously, you want the crew to be able to communicate during an emergency, so you'll have radios that do this. And to extend that too, in some cases, some of these basic flight instruments or radios may have their own backup batteries separate from the aircraft emergency battery. And so if that's the case, then there's things known as integrated standby instruments that don't even pull any power from these emergency generators, but rather have their own backup battery. So those are the secondary sources we have available, as well as the emergency sources, and then the load shedding that's needed in order to match loads to those emergency sources.